over rotational momentum. Let's begin. So let's start off with the translational version of momentum, where P represents translational momentum is equal to the object mass times its velocity. And the important thing is I'm including those vector hats because direction matters. Which is to say that an object moving to the left has a momentum to the left versus an object that's moving to the right has a momentum to the right, right? So that direction part is important. Like we did in the other parts of the rotation unit, we can actually come up with the rotational momentum formula based off the translational one. So instead of saying M for rotational, we say it is I for rotational inertia. Instead of saying V, we say it's omega. And it's important that omega also has a direction, and the variable that we use for rotational momentum is the capital letter L. Okay, much like translational momentum, rotational momentum direction also matters, and it is a vector. And the reason why I'm trying to make an emphasis of this is in order to find the direction, you have to use the right-hand rule to determine the direction of the spin. Remember, we can't just call it clockwise versus counterclockwise, right? We have to use the right-hand rule. All right, so this is actually version 1 of the formula, and for this version of the formula, what you're looking for are what we call rigid bodies, or things like disks, right? Like actual objects, or like rods, or like cylinders, okay, or like hoops, right? So specific objects that is spinning around. All right, so let's go into version 2 of this formula, and we're actually going to get version 2 from a derivation of version 1. So for version 2 of the formula, what you're looking for is a point particle. So if we were to do a sketch of this scenario, we would have an axis of rotation right there, okay? And we would have a point particle, and this point particle is going to be moving around in a circle, like so. So what we can say is for this point particle, let's just say this object is moving up with a translational velocity, vt, and it is at a distance away from the axis of rotation called r. Now, let's start off our derivation with the rotational momentum formula. L is equal to I omega. Our rotational inertia formula for a point particle is mr squared. And to go from rotational velocity to translational velocity, we have to use this formula here, and we see that it is v over r. And through the use of algebra, we see that this turns into mrv, but for the sake of our discussion, I'm going to rearrange those variables to get mv times r. And you can see here that we have translational momentum in the rotational momentum formula. So rotational momentum is equal to the translational momentum times the distance away from the axis of rotation. And this moment right here is actually really big, so big that I want to leave us a little note. What this is telling us is objects moving in a straight line is said to have rotational momentum. All right, so even though it's moving in a translational fashion, based on the frame of reference, we can say it actually has angular momentum. All right, now the specific case that we looked at is for a point particle that's moving in a circle, and for this specific case, the shortcut formula that we can use is L is equal to mv. Okay, and we can keep on using this formula, but you need to understand that this is actually a shortened version of the official formula. All right, so let's take a look at the longer version of this formula. All right, so this is going to be part 3. So for this part, I want to first start off with the sketch of that's describing the thing that I just typed out, that an object that has translational momentum actually has rotational momentum. So let's begin our journey by drawing the axis of rotation right there. So if that's our axis of rotation, and this is our object M right here, and it has a forward velocity of v. Okay. Now, this specific moment in time is directly linked to what we just discussed, meaning that if you take a look, this axis here, this is my r, okay, and my r is actually a vector, and I'm going to show you my vector like so. Okay, this is my r vector, and it's going directly to the axis of rotation, and my mv is my momentum, and momentum is also a vector, so I'm going to draw my momentum vector right below it. So this is my momentum vector. Now, the important thing that I want to point out is that my r vector and my momentum vector is at a 90-degree angle. All right, so here we go again with that 90-degree angle. So for those of you that have been following along, whenever we see a 90 degree, that's actually a cross product. And so the official version of the formula would be r cross product momentum. So we have maximum, so this is, so when theta is equal to 90, we have quote unquote maximum rotational momentum. Okay, and I'm going to go a little bit more into that detail, what I mean by maximum rotational momentum. So the important thing is we can use L is equal to mvr, but if you're like, wait a minute, Mr. Lee, what about the cross product? Right, I forgot, cross product is sine of theta. But because this is sine of 90, the sine of theta is actually 1, and that is how we got just mvr. Okay, so now you can see, right, even though the formula is mvr, there's a sine of theta that is attached to it, which fully explains the problem. So let's go into the sine of theta, all right? Now, if we were to rewind time, okay, because this object is moving to the right, if we were to rewind time, we would say, okay, so the object was there, but we can also say, if we were to rewind time, the object started there. And so the object starts here, and it has a forward velocity this way. Now, I'm going to resketch this in a little bit. So let me just explain this drawing first, and we'll go into the cleaned up version, and we'll continue notes from the cleaned up version. And so we can say that here, this object still has a forward momentum here, but our radius is different. If this is our radial vector, we can say that our radial vector is, so this r, let's call this RA, and this is r, just regular r. We can now say that RA is greater than regular r, okay? And so when we, like, quote unquote, went back in time to where this object first began, all the way to the left, okay, it was further away from this axis of rotation, and our hypotenuse was bigger. But if we're following along this angle here, this 90 degrees, that's created between your radius vector and your momentum vector, we can now see that our angle is no longer 90 degrees, but our angle is just less than 90, so theta, right? So this is, so let me recreate this image below. So if you're recreating this image here, this is our axis of rotation. Let's draw your object over here, and this object is moving forward with a velocity of v, and this object is at a radial distance r away. All right, and of course, can't forget that our r is a vector there. So if we are looking at our formula, rotational momentum is equal to m times v, excuse me, let's start off with the official formula first, r cross product p, so r sine theta mv, right? If I were to just make it look from one form to the next. Let's describe this right here, r sine theta. So for those of you that, if you're like really into trigonometry, you already know what r sine theta means. But essentially what I did is I'm saying that in this image here, we could actually view this image as a right triangle. Okay, and if we know that this right here is our theta, the question is, where is your r sine theta? So we know sine is, so the trig identity of sine theta is opposite over the hypotenuse. And in our example problem here, our hypotenuse is just r, and what we're solving for is the opposite sign. Meaning, if I were to rearrange this formula here, I will get the opposite side is equal to r sine theta. And r sine theta is right there. This is r sine theta. And if you remember, the important thing about that length of the triangle is r sine theta is the r when the object is right there. Okay. Now, if I were to give you more details, r sine theta is the distance r when the object's radius and momentum are at a 90-degree angle. Okay? So this is the shortest distance between the axis of rotation and the momentum if the object is moving tangentially along that path. So to figure out, hey, where is my theta angle? You have to ask yourself, if this object to be moving in a straight line, when is it the closest to the axis of rotation? Okay, so that will be your r sine theta, and you have to multiply that by your momentum. Let's do a quick separate example. So for example, if we have a axis of rotation right there, so we just saw something that's moving side to side, what if you have an object that is up here and it's moving downwards? All right. So this is our object and it is moving downwards. So what I'm going to do, right? So this is my problem solving strategies. I'm just going to trace the path of the object. Okay. And what you're looking for is when the object's path is perpendicular to the radius. So if this is the path, the radius perpendicular to that path would be right there. And now I'm going to fill out the rest of my triangle. So this is my actual r distance. And r sine theta is opposite, or r sine theta is that perpendicular path. So this is r sine theta, which makes this your angle. All right? Okay. So we just talked about the three different versions of rotational momentum, which is just one version that can be derived. But the important thing is that this here, this version of the formula, we're using this for a point particle moving in a straight path. All right. The last bit of notes is going to be impulse. And this is just a review from our previous idea of impulse. So we know that impulse for translational is the change in momentum, and we use the capital letter J. So for rotational impulse, it's just the change in rotational momentum, and I'm going to put a little subscript R there. Okay, but the important thing is the following. First, you have to identify the system. Okay, so let's say you have two different objects. You have a bar and you have a ball. Now, if our system includes both the ball and the bar, the impulse of the system is equal to 0. Now, as a reminder, impulse is the force times the time, which is J. So we could rewrite this as torque times the change in time for rotational impulse. Now, the reason why we can say the system's impulse is 0 is because the impulse of the rod, okay, if it's going to gain a momentum or lose momentum, is the same as the J for the ball. So JB is equal to the J of the rod. So the overall system's impulse would be 0, because if one gains momentum, the other one has to lose momentum. And the idea comes from this here, right? So remember, you can't exert a force on yourself. The force has to come from an outside source. And so if one object exerts a force on the other, it's a equal but opposite on the other object, all right?